So the idea of stress is that we have some internal force that we're essentially distributing across some area, or it's kind of being carried by an area. So you can see right here I've got a beam. It's got a load of P on each side, so it has an internal normal force N, which would have to equal P in this case. And then we're saying that this stress, which we use the letter sigma for a normal stress, has to be basically this load N distributed across the cross-sectional area. So to say that more clearly, we say that the normal stress, which we call sigma, and then I guess I just use a lowercase n here for some reason, has to equal the internal force divided by the area that it's distributed across. And so this is one of the types of stress we're going to have. There are other types of stress, but the basic idea for all of them is that we have some internal load that's being supported by some area. And the ones that we're going to look at in this specific video are going to have the assumptions of a prismatic bar. Now, prismatic is basically a way of saying that there are three kind of sub-assumptions that we have here. So the first one is that we're looking at a straight bar. Another way to say this is that it's axially loaded. So if you'd imagine right here, basically we have a support here on this side, right, that's pulling, and then we have the load that's actually pulling on it. But if we were to say have a beam that looked like this, and it was kind of like fixed at one end, and then let's say I put a load like vertically instead of axially, so I did something like this, well, just kind of intuitively, you kind of know that it would want to bend upwards, and that's because there's not something that's essentially in line with this force to support it. So like if I had a support here, then we would be able to say that there's a compressive normal stress in this area right here, in this slice, right? In the area that you would get from basically slicing it, like if I took this area right here, right? But if there wasn't a support there, then what I would have is it would basically kind of bend upwards like this, right? It wouldn't have that normal stress. Now the other assumptions are homogeneous. So that basically just means that it's well mixed. So you're not going to have a portion that has higher density or some kind of different property. Basically the properties are uniform throughout, and also the properties are the same in every direction. This is called isotropic. So right, I'm not going to have like a different property perpendicular to my axis versus along my axis. In every direction, the properties are the same, which means that we can find the stress the same way. Now, when we're talking about units, we already said that it's force over area, right? So my units for all types of stress are going to be force over area. So my force, let's just talk about the SI system first, is going to be my units of force, which are newtons, over my area, which is meters squared. And this is called the Pascal. Now, when we're talking about solid mechanics, usually the Pascal is a little bit too small. So instead, what we're going to use is the megapascal, which if you think about the prefixes, mega means million, so this is 10 to the 6th pascals. Then we also have the gigapascal, which is 10 to the 9th pascals. And the reason this is useful is because usually what you're going to have is basically your force is going to be given in either newtons or kilonewtons, and then your area is probably going to be in terms of millimeters, right? If you think about like a bar that you would actually see, it's usually not like meters wide, or it's too small to be measured in square meters, right? So usually what you'll have is you'll either have newtons per millimeter squared, which if you think about this, a millimeter is 10 to the minus 3, 1/1000th of a meter. So this is 10 to the minus 3 meters squared. And then we have newtons here, which is right here. If we have a 1 over 10 to the minus 3 squared, that's the same as 1 over 10 to the minus 6, which is 10 to the positive 6. So when you combine all this, what you get is 10 to the 6th newtons per square meter, which is the same thing as a megapascal, right, from right up here. And now a kilonewton, well, a kilonewton is 1,000 newtons, again, from the prefixes. So this is 10 to the 3rd newtons. So if we have a kilonewton per millimeter squared, then what we would get, I guess we'll just do this, is, well, we would have 10 to the 6th times, and we'd have a 10 to the 3rd because we have 1,000 newtons per per meter squared, right? 10 to the 6th times 10 to the 3rd is 10 to the 9th, so this right here is a gigapascal. So you can see right here, depending on what we're given, it's going to be useful to use gigapascals or megapascals usually. And then we also have the imperial system to deal with. So just real quick to run through this. Our unit of force is the pound force. Our unit of mass is the pound mass. Our area is inches squared. So if we have pounds force per inches squared, that's a pound per square inch, or we say PSI. 1,000 pounds is called a kilopound. We write out kip. So kilopound per square inch is a KSI, kilopound per square inch. And then lastly, sometimes they'll give you terms of length in feet. So if you need to convert from feet to inches, 1 foot is 12 inches. And that's going to be it for the imperial system. So now we can talk about the types of stress. We already saw one of them. It's the normal stress. But if you imagine, like if this is my area right here, there's two kinds of stress I could have, right? I could have it coming away from it. This is in the normal direction. Or it could be parallel to this. I mean, technically it can be in any direction, right? I could put a force this way. I could put a force this way. But I could always express this as a combination of forces that are perpendicular, either outward in tension, which is our convention for the normal, or it could be inward towards the surface in compression. And then we also have this parallel component, which is called the shear stress. We call it V. So if you imagine like I have a little square of my element right here, right? A positive normal stress in tension right here basically wants to stretch it out, right? So my outcome would be something that looks kind of like this, right? And if I had a negative normal stress, then what would happen is it would kind of get squished in. So it would basically end up looking like this, right? If I had a normal force pointing in like this, because it's compressive. Now the shear, what it looks like is basically it kind of wants to squish it into a parallelogram. So basically, if this is my original square, I'm kind of running out of room here. Why don't we go to the side? So if I have my square right here, and I do a shear force that's going to be parallel to my surface, then what it wants to do is basically shift the top portion of it to the right like this. So this is actually like if you've taken linear algebra before, you might recognize the shear transformation, and this is where it comes from. So we have the shear force that's basically a load being carried by this area right here. And now I said area earlier, but this is technically a line. So when you go into 3 dimensions, you're going to have an area that looks something like this, right? So you can still have your normal component of your force pointing perpendicular to the surface, but now we'll have 2 parallel components. We'll have a shear in 2 directions, so usually we'll just give these subscripts. So this would be like our shear in the x and our shear in the y, for example. So these are our 2 types of stress. We have our normal and we have our shear. And as we go through the course, we're going to see that there's all types of different stress. So we already looked at axial normal stress, but there are other types. We're going to have something called bearing and bending. And then for shear, we're going to have direct, transverse, tearout, and torsional. So let's take a look at an example of our axial normal stress. So you can see right here I've got an object and I've got some different forces acting on it. There's one here, 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 and here, acting at different points. And depending on which section of the beam I'm looking at, either between A and B, between B and C, or between C and D, there's going to be a different internal axial normal stress. And now because of statics, if you just go ahead and take a look at the forces, you can see that they should balance out, right? So I have 300, 350, 400 to the left, and 400 to the right. Any section, I can look at either side of it to determine which force is going to be acting inside of it. So basically, let's say I want to look between B and C, right? I know that I'm going to have a force here to the left of 300 kilonewtons. And then I'm also going to have a force here to the right of 400 kilonewtons. And then lastly, I have my internal normal force, right? So if I go ahead and I add up all the forces, and let's just call this to the right the x direction, then I know this has to equal 0 because we're in equilibrium, and that has to equal our normal force plus this 400 minus this 300 kilonewtons. And now if I solve for my n, I can see that my n is a negative 100 kilonewtons. And if I wanted to, I could have done it with the same thing on the other side. So basically my free body diagram of the right side would have looked like this. I would have had my cutout right here. I would have had a 50 to the left and a 50 to the left right here. And then I would have had my internal normal force looking like this. And I would have gotten the same thing, negative 100. This negative just means that it's compressive, and now we can go ahead and come over here and solve for the internal normal stress. So this is our normal force divided by the area, which of course equals this we just found, negative 100 kilonewtons, divided by our area is given, it's 2,000 millimeters squared. Now if you remember, this is going to be a negative 1/2 kilonewtons per millimeter squared, which is the same thing as a negative 0.5 gigapascals, and that right there is our answer. We could have done the same thing between points A and B and between points C and D. My bad, this should be 1/20th, which would mean that this is actually a 0.05 right here. Now in reality, if you're going to go build something, let's say you're building, I don't know, a bridge, right? And you go ahead and you figure out, okay, based on what I know about like the weight of people and how many people are going to be on this or whatever I'm going to have on this bridge, let's just say that you imagine that your ideal kind of stress is going to be whatever, let's just say like 500 gigapascals, okay? Now in a real world application, it's not good enough to basically engineer this bridge so that it can only take 500 gigapascals, because you don't actually know what's going to happen, right? What if it exceeds the weight limit slightly? What if there's some problem, stuff happens? We need some way to ensure that this isn't going to break on us. And one thing we could do is introduce a factor of safety. So for a bridge, usually a factor of safety is usually something like, 5 to 7. We could just go ahead and say, 3 seems good. Less than 1 means that your thing is broken. It should never be less than 1. So basically what we're saying is that ideally this should never have to take more than 500 gigapascals. But I'm going to design it so that actually it can take up to 1500 gigapascals. And what we've actually shown here is what's called the design factor. So basically this is what we ideally want. So ideally, this should take 500 gigapascals in real use. We're going to give it a factor of safety of 3 to give us 1500 gigapascals. So this right here would be better called the design factor. The actual factor of safety is basically equal to our yielding, or basically the stress that it can take before it just breaks. So this would be 1500 in this case, divided by what it's actually taking. So, let's just say it actually takes like 500 gigapascals, maybe our approximation was right, and then this would be in the denominator, and then we'd have in the numerator of 1500. Maybe I won't use the same number just so you can actually see how these two things are different. So let's say all of this is in the design, and then let's say that actually it's like 550, right? If you do 1500 divided by 550, you get like 2.73-ish. So this right here would be your factor of safety, and then this would be the design factor of safety. Now let's go ahead and take a look at how a direct shear stress would work. So basically the idea here is that the plane that's taking the shear stress, so remember that if we have our little cube here and we have a force on top, then what that's going to want to do, if this is our bearing area, or the area that's taking the load down here, it's going to basically want to turn it into a parallelogram like this, right? So the green part right here is the area that we want to be looking at. So basically for this pin right here, where we essentially have a beam that has a load to the right of P and a load to the left of P, this would be our area that's basically stopping that shearing from happening. And then here where we have a double shear setup, we have a P here, and then we have a P over 2 on the top and bottom so that our force is balanced. We would actually have 2 areas where it's shearing. So the shear stress, again, is just equal to the force over area. So force over area, except now our area is parallel to our force. So if we go ahead and look at this beam right here, for example, we would have our P divided by the area of whatever this little cross-section of this blue thing happens to be. But in the case of this double shear joint, what we would have is, let's say that you look at this little beam in the center right here, right? I have this load P, and the area that the shearing is distributed across is this area right here, and also this area right here. So for this part, I would have our shear stress, which is the letter tau, equals P over 2A. Another way you could look at this is, let's say I look at this top beam, right? I know that the load that it has to carry is P over 2, right? This cross-sectional area has to support a load of P over 2 by basically having a reaction in this direction. So I know that P over 2 has to be supported by the area the cross-sectional area of this bolt right here, A. So I'd have a P over 2 over A, which is just the same thing as P over 2A. So no matter which beam you're looking at, the shear stress for this case is P over 2A. So at this point, we looked at the two direct cases of normal and shear stress, axial and direct, and now what we're going to look at is some of the cases it can fail in. So for a normal stress, we'll have something called bearing, and for our shear stress, we'll have something called tear out. So let's go ahead and start with bearing. The idea here is that if I have essentially some slot right here with a pin going through it, so if you imagine this in 3D, we kind of have like a little pin right here, right? Coming through and kind of projecting through it like this, where this right here is our hole. And there's a force being acted onto the slot by the pin, and if it fails, if it yields, then it can kind of stretch through it like this, right? So basically what we'd have is if we looked at the little circular area of our bearing pin, we would have something like this, and it would have some thickness. So it would look a little bit like this. This isn't the greatest drawing because it's like a curve in 3D. But you see what I mean? Basically, into and out of the screen, we have a thickness right here of T, and then this is a circle right here, so we'd have a diameter right here of D. Let's go ahead and draw this in 2D since it'll be a little bit easier to see. We have our object, which is just a semicircle. That's what's going to end up taking this load. And then this load P is being kind of directed onto our slot by the pin, right? And now actually examining the normal stress of this would be pretty difficult because it's not all perpendicular, right? So like right here, we would just have a direct P over A, but here there would technically be almost no normal stress at the top or the bottom. Here there would be a little bit more, and it would be maximum right here. And the book basically says that it's close enough to approximate this as just a rectangular area. So basically we're going to assume that the area is close enough to a rectangular area taking this load right here, P, to where the error is negligible, right? So we still have our thickness right here, T, and our diameter, D, and we're saying that the bearing stress that this thing has to support is our P divided by the area, which is equal to T times D. Now for the shear failure, we're going to have something called tear out. And the idea here is that if you imagine we have our beam right here, this is a rectangular beam, and then it has a slot right here, which is where a pin is coming in, and this pin is basically exerting a force in this direction. If it turns out that these areas right here, so this area above it going out to the edge, and this area below it going out to the edge, if both of these can fail in shear, then what can happen is this entire little like thing right here, this little chunk of it, can just pop out, and basically then it's broken out, right? The pin no longer works because there's just a gaping hole in our assembly. So we know that the shear stress in this case is going to be equal to our force, which is, we're just going to call it P, divided by the area of the tear out. So it'll be the area of this plate plus the area of this plate. So we'll just call this area tear out. Now the area of our tear out is going to be equal to, we're calling this right here X. So the X goes from the edge to the center of our pin, and then our pin has a radius R. So if we go ahead and we do X minus R, that will give us essentially the length right here of this red. And then if we multiply this by T, what we get is the area of one of these. So we go ahead and multiply it by 2, and this right here is the area of the tear out. Now another case we can have is basically a rounded end right here, where basically you can see we have a pin right here, and then it's rounded off. And in this case, the length of the tear out is a little bit harder to get, and it doesn't make a whole lot of intuitive sense. So in this case, right, we're basically saying that once the edge of this circle gets to here, once it gets past here, the entire thing can just pop out. But here, the length of the tear out is going from basically the top right corner of the bounding area of this circle to where it meets the edge of this outer circle right here, which wouldn't technically remove all the material. But again, this is just an approximation. We're assuming that all of the force is acting perpendicular to a rectangular section of it anyway. And most of these cases, what you're actually looking at is empirically derived formulas that are close enough. So anyway, in this case, the length of the tear out is going to be the length of this dotted line right here. So the area of the tear out is going to be that times the thickness. So we can see right here that our x is going to be equal to, by the Pythagorean theorem, we're going to have the square root of our big radius squared minus our little radius squared. Basically, so big radius is going to be the hypotenuse right here, and then little radius is one of the adjacent sides. So another way we can write this is that x squared plus r squared has to equal big R squared. If I subtract this over and then take the square root, I'm going to go ahead and be able to get x right there. And now x minus lowercase r will give me the length L that I'm looking for. So the area of the tearout is going to equal 2 times x minus little r times our thickness t. And then the shear stress is just going to equal P divided by the area of that tearout. Now I know that earlier when I talked about normal stress, I looked at basically this kind of axially loaded bar where we have a load on each side that's parallel to the axis, which runs along it. But we also can have shear stress if we look at an inclined surface instead of just the perpendicular surface, right? So if I look at my perpendicular surface, I would just have an internal force like this. But if I looked at an angled one, I would have both a normal and a shear force that would contribute to the entire internal force. So if we want to find the normal and shear stress, then we just have to do a little bit of trigonometry here. We can go ahead and call the area of this like slanted plane, I don't know, we can call it like A prime or something. Now we'll have a triangle right here like this, right? So this is our angle theta. Right here is A. Our hypotenuse is A prime. So the cosine theta is adjacent over hypotenuse. We get an A over A prime, which means that our A prime has to equal A over cosine theta. Now, if you recall from geometry, I think there's this thing about opposite interior angles, I think is what they're called. So basically the idea is that if I have two parallel lines and then I have a line that intersects both of them, these angles right here have to be the same. And then also these angles right here have to be the same. So if we go ahead and we look at our setup right here, what we can say is that if we have a vertical line right here, then this angle right here has to be the same as theta, which means that this angle right here, if we go ahead, the whole thing has to add up to 90 degrees, which means this part right here is 90 minus theta. And then this angle right here, again, this total 90 minus theta plus whatever angle we're trying to figure out now has to add up to 90. So we can say 90 has to equal 90 minus theta plus our new angle. We'll just call this like, I don't know, alpha. Okay. Now we can subtract 90 from both sides and add over the theta. We find that alpha has to equal theta, which means this little angle right here is theta. All right, now if we bring out this triangle, what we have is we have our normal force, our shear force, and our load P. Bro, switch colors. Ah! So these are perpendicular, and then this angle right here is theta. All right, normal force right here. Normal force. Oh my god, bro. Switch goddamn colors. And then we have our normal force, our shear, and our load. So we can say that the cosine of theta has to equal adjacent over hypotenuse, which is a normal force over P. And therefore our normal force is a P cosine theta. Then we can also say that our sine of theta has to equal opposite over hypotenuse, which is shear over the load. And therefore our shear force has to equal P times the sine of theta. And now I can go ahead and get my normal and shear stress real quick. So our normal stress is equal to N over A, which equals P cosine theta. I guess this should be an A prime, since we called this right here our A, since we found that right here. And then we also have our A prime, which is an A over cosine theta. All of this is in the denominator. That's a terrible C. And then if we go ahead and simplify this, what we'll get is a P over A cosine squared theta. Now for the shear force, we have our shear force divided by A prime, which is going to equal our P sine theta over the quantity A over cosine theta, which equals a P over A times the sine of theta times the cosine of theta. And so now that we've looked at a couple of the specific cases of normal and shear stress, I think it makes sense to talk about the generalized case, which is called the stress element. So the idea here is that we have some small section of our thing that's in stress, so either a square in the 2D case or a cube in the 3D case, and it's going to be subjected to both shear and normal forces, which we're going to write as stresses. So our sign convention is that the normal forces are going to be pointing away, so we're going to have a normal force right here, we're going to have a normal force right here, and we're also going to have a normal force right here. And because this has to be in equilibrium, there's also going to be a matching one on both sides. So we have to have one coming out this way, right, and one coming out this way, and one coming out this way. But I'm not going to draw those just because the diagram would get really cluttered. So we call this sigma x because it's on the x face. This is sigma z and sigma y. Now for our shear force, there's going to be two components since we're in 3 dimensions. And our sign convention is to write them in the positive, positive, or negative, negative direction. So since we're on the positive x face, I would have a shear force in the positive x face in the positive z direction. And the naming convention here is to write tau x z because we're on the x face and the z direction. And then we'll also have one pointing up. And this will be tau x y since we're in the y direction. Now for the other ones, we'll have tau zx and tau zy. And then here we'll have a tau yx and a tau xy. And then one thing you could do is you could write up all these stresses on a nice little matrix. So basically you would have like our stress in the x, stress in the y, stress in the z, and then you'd get your shear force in the x and the y direction, and then the yz, and then here you'd have, right, yx, yz, this should be an xz. And then lastly, we'd have a tau zx and a tau zy, just like this. And then what you could do is you could say if you have a normal vector, like some vector pointing in some direction, if you take that normal vector and you dot it with this thing, it's called the stress tensor, then what you would get is something called the stress vector, which points in the direction of the generalized state of stress. But for some reason, apparently, linear algebra isn't a required course for engineers, which means that stupid school, which means that we actually can't use this super cool stuff, and instead we just have to do the boring 2D crap. So, I guess just ignore this, but it is really cool. Like if you want to go further, there's a lot of cool stuff you could do with this. But because we can't use linear algebra, this is technically outside the scope of the course, but because you can sum up all the moments and the angular momentum across any axis, not just the x and y, so what you would do is basically, let's say you pick the z-axis, right? If I sum my moments, I would have like a length in the x, so maybe we just call this like a dx, or maybe delta x, so we'd have like a delta x times this shear in the xy, right? And then times the area that is acting across, so we'd have a delta y and a delta z because that would be the area of this face. Just as one example, you would have to add it up for every single axis in every direction. But if you do that, what you get is that the shear forces have to be equal and opposite across any axis. So, for example, let's say I'm looking at the z-axis right here, and this would be a good time to use the 2D case. So I'm going to have my sigma x, right, normal stress. It'll point out this way, and then I'll also have one like this. And then I'll also have my y. And then I'll have my shear, so I'll have a shear xy, xy, and then I'll have a shear yx up here, right? And then down here, it'll be in negative direction, so the negative y and the negative x direction. This is shear yx. And then we'll also have a shear xy. Same thing. But here is saying that all of these shears, the yx, the xy, all of these have to be equal because all of the moments have to cancel out across any axis. So what you would actually get is that there are only 6 unknowns you would have. You'd have this normal stress in the x, the y, and the z, which have to be the same on both sides. And then you'd have the shear stress in the xy, you'd have the shear stress in the zy, and then the shear stress in the xz. And across that entire loop, they would have to be equal and opposite to each other. And so now that we've talked about the general case of stress, we can look at what happens when we start to angle it. So if we go ahead and basically we look at a wedge, which is done by taking an angle, kind of like a slice out of this, then what we would have is that that wedge would have its own shear and normal stress in the direction basically parallel to this hypotenuse and perpendicular to it. And then if we look at the areas, we're going to go ahead and call this angled area dA, and then this angled area right here would have to be dA times the cosine of theta, and this one down here would have to be dA times the sine of theta. And so now what we're going to do is we're going to sum all of the forces in the normal direction which result from these stresses. But real quick, I think it might be a good idea just to draw all the forces that are happening real quick. So we're going to have our normal right here. We're going to have our tangential direction right here. We know that the angle from horizontal that we've rotated this is theta. So we can go and call this angle right here theta. And if we go ahead and continue our axes, and we'll also go ahead and add vertical axes real quick. Our forces that we're going to have, or I guess our stresses, they'll be pointing in the same direction, so it doesn't really matter too much, is we'll have our sigma normal right here, right? We're also going to have a shear that actually isn't going to be in the normal direction at all, so we're just going to basically ignore it for this part. So next we'll have our sigma x right here pointing to the left. We'll also have our sigma y pointing downward. And then we'll have our shear xy also pointing to the left. And then lastly, we'll have our shear xy pointing downward. My bad, this should be a yx. So I'll have a yx right here. And then my shear xy pointing downward. So now if we go ahead and we add up all of the forces in the normal direction, since it's an equilibrium, we know this has to equal 0. So this is first going to equal our normal stress times our dA, because remember, stress times area gives you force. We're calling dA the area of the slanted section right here, basically. You can see right here. Now let's go ahead and add these up. First, let's do, shear yx. So we're going to have a negative shear yx because it's going to be pointing in the negative normal direction. So we'll have a negative shear yx times the sine of theta. Because it's on the bottom right here, we're going to have a sine theta. So I guess we can go ahead and just call this dA sine theta. So we'll have a dA sine theta. And then we'll also have to multiply this by a cosine of theta in order to project this onto our normal axis. Now, for our shear xy, it's also going to be in the negative direction. Our shear xy is in the vertical direction, so we're going to have a dA cosine theta. So we'll put a dA cosine theta. And then we're going to have to multiply by the sine of theta to again project it right here, because if you imagine this right here is in the horizontal direction, so we use a cosine to get it from here to here, and then this is in the vertical direction, so it's going to be a sine because it's related to the opposite if we have a triangle right here. Now for our normal stresses, we're going to have to subtract our sigma x. If we look at our sigma x right here, it's pointing in the negative normal direction, times, we're going to have a dA cosine theta times another cosine theta, 1 to project them and 1 because the area that it's on, this area right here, is a dA cosine theta. And then for our sigma y, we're going to have a dA sine theta because it's on the area on the bottom right here, which has that dA sine theta. And then we're going to have another sine theta to project it onto the normal axis. Now what we can go ahead and do right here is we could just divide everything through by a dA. All of the dA terms are going to cancel. And then if we go ahead and we solve this for the normal stress in the rotated state, we'd basically add everything over. What we'd have is we'd have our normal stress is equal to sigma x times cosine squared theta plus sigma y sine squared theta plus, now remember that our shear yx and our shear xy are the same, and then both of them have a sine and a cosine term, so we're going to combine those into 2 shear in the xy plane sine theta cosine theta. Now to simplify this, we're going to use some trig identities, and normally I would just show you what they are, but I think every once in a while it's helpful to kind of take a look at how these are derived and make sure that they still make sense to you. So let's go ahead and do that. Now this is one of the times I think it would actually make sense to use an animation just because it's a little bit easier to see things if they're animated. So we know that e to the x is the function such that, when you take its derivative, you just get e to the x. And if we use the chain rule, then we can see that if basically you have e to the ix, we take the derivative, we're going to get an I term out of there. Now in the complex plane, multiplying by I is the same as rotating it by 90 degrees. So the way you can think of this is that our velocity always has to be a 90-degree rotation of our position. Now if we go ahead and animate this, you can see that the path that best fits this description is a circle, right? So we can say that e to the ix has to equal the path that's being traced out by the circle. Now if we also use the fact that e to the 0 has to equal 1, then we can say that our x-axis has to basically oscillate between 1, starting at 1, between 1 and negative 1. So we go and use the cosine of x to do that. And then our y-axis starts at 0, it goes up to 1, and then between basically positive 1 and negative 1 again. So we could use the sine of x. And then you can see that if we add these two effects together, they end up tracing out the circle that we're looking for. So now instead of t, we can use the sum of two angles a and b, right? So we see e to the I times a plus b has to equal, cosine of a plus b, right? This is just by Euler's formula times times the sine of a plus b. We can also manipulate this side of the equation, right? Because we also know that this has to equal e to the ia plus ib, which is the same thing as e to the ia times e to the ib, right? Because adding powers is the same as just multiplying by the same powers, right? If you imagine we have like e to the 2 plus 3, which is equal to e times itself 5 times, which is the same as e times itself 2 times e times itself 3 times. It's a lot of times in the same sentence, but I think you get what I mean. So anyway, this has to equal, right? And then we'd have a cosine a plus I times the sine of b. That would be, this should be a. All of this has to be multiplied again by this this right side right here. So we'd have cosine of b plus I times the sine of b. And now we can go ahead and distribute this out. So the first two terms will give us a cosine a, cosine b. And then we'll do the outer terms. So we'll have an I, cosine a sine b. The inner terms will give us an I, sine of a, cosine of b. And then the last two terms, we have two i's, so that's going to give us a negative 1 times the sine of a times the sine of b. And now what we can do is we can group together our I terms and our non-I terms. So this is equal to cosine a times the cosine of b minus the sine of a times the sine of b plus I times the cosine of a times the sine of b plus the sine of a times the cosine of b. Now remember, back up at the start, we said that this has to equal cosine a plus b plus I times sine a plus b. And since the complex part and the real part have to equal each other, we can combine these and say that cosine of a plus b, which is the real part of this expression right here, right, has to equal all of this stuff. So cosine a, cosine b, minus sine a, sine b. And the sine of a plus b, which was the imaginary part of this expression right here, has to equal the imaginary part of this expression. So we'll have a cosine a sine b plus sine a cosine b. And this right here is the equation for the added angle formulas. Next, we're going to go ahead and do Pythagorean identities. So if I have some triangle that looks like this, and I have an angle theta, so we'll call this is a right triangle, radius of r, and then this right here is the angle theta. So we can say that the cosine of theta, right, by definition has to equal the adjacent divided by the hypotenuse, and therefore the adjacent has to equal r cosine theta. So we can go and put the adjacent side here is r cosine theta, and then the same thing for sine. We'll say sine theta has to equal the opposite over the hypotenuse, and therefore the opposite has to equal r times sine theta. So we put in r times sine theta right here. And then by the Pythagorean theorem, which we're not going to bother proving right now. I know there's a proof for it. Go ahead and find it yourself. The problem is we'd have proofs all the way down, right? Like, it depends on how far back you want to go. Here I'm just trying to give you an idea of where these concepts come from, because I think it's a lot better to understand concepts than memorize like all these random trig identities. So if you understand concepts, and then some things you just kind of pick up along the way, like the Pythagorean theorem, but there always is a proof. It's just not always worth the time to go through the proof of every little single thing, right? So anyway, we have that a squared plus b squared has to equal c squared. So we could say that r cos theta squared plus r sine theta squared has to equal r squared, which if we go ahead and we distribute this across, this will give us an r squared cosine squared theta plus r squared sine squared theta has to equal an r squared. And then we just divide through an r squared on everything, and we get that the cosine squared theta plus the sine squared of theta has to equal 1. And now we can actually start getting to the identities. So first we're going to go ahead and do the cosine squared identity. So basically, if you remember back, we had the added angle identities. I'll just go ahead and copy it down right here. So we had that the cosine of two angles added together, a plus b, has to equal cos A, cos B, minus sine A, sine B. And now what we're going to go ahead and do is just let A equal B. It's pretty simple. So we can say that the cosine of 2A, because A equals B, so A plus B is just 2A, has to equal cosine A. We're just going to replace everything with A now. Cosine A minus sine A, which means that this has to equal cosine squared A minus sine squared A. And now what we're going to go ahead and do is substitute in the Pythagorean. So remember, cosine squared plus sine squared has to equal 1, and therefore sine squared is 1 minus cosine squared, which we're going to go ahead and substitute in right here. So we get that this has to equal cosine squared A minus the quantity 1 minus cosine squared A, and if you distribute across that negative sign, this is equal to a 2 cosine squared A minus 1. And now if we go ahead and we add the 1 over and divide by 2, we can solve for cosine squared of some angle A has to equal 1/2 times 1 plus the cosine of 2A. All right? And now we can go ahead and leverage this to get that the sine squared identity has to equal, based upon this right here, if we go ahead and we, all right, let's just go ahead and start with what we know. We know the Pythagorean, right? Sine squared plus cosine squared has to equal 1. And now we're going to substitute this in. So we get that the sine squared theta plus half times 1 plus cosine of 2 theta has to equal 1. Let's just go ahead and call this A to be consistent with the other one. You can call it theta or you can call it A. It's just a placeholder for our angle, right? So now what I'm going to do is I'm going to subtract this over, which means that I'm going to get a minus cosine of 2A. But since I'm adding 1, this one term is going to stay positive, which means that the sine squared of A has to equal 1/2 times 1 minus the cosine of 2A. And now lastly, the last simplification we're going to do has to do with that sine of theta, cosine theta term that we had, right? So what we're going to do is we're going to start with the added angle identity for sine. So I guess I should just say 6. This is the sine theta, cosine theta. We're going to start with the added angle identity for sine. I'll just go ahead and copy it down real quick. Now we're going to do the special case that we let A equal B, which means that we're going to get the sine of 2A because A and B are equal, has to equal, and then again we're just going to replace everything here with A, so we'll get cosine A sine A plus sine A cosine A, and these are two ways of writing the same thing, which means that we can say that our sine of 2A has to equal 2 sine of A, cosine of A. And that right there is where we're going to leave it. And so now we can come back to where we were, and we can use those trig identities to simplify. Right, so this is going to equal sigma x times 1/2, 1 plus the cosine of 2 theta, and then we're going to have a sigma y times 1/2, 1 minus the cosine of 2 theta, and then we can replace this 2 sine theta cosine theta with a plus shear times the sine of 2 theta. And now what we're going to go ahead and do is we're going to take this half sigma x and this half sigma y and combine them. So we're going to have sigma x plus sigma y over 2. This should be a plus sign, my bad. So now notice that we have a 1/2 sigma x cosine and a negative 1/2 sigma y cosine as well. So we're going to go ahead and combine these. We're going to have a sigma x minus sigma y over 2 cosine of 2 theta. And then we're going to have plus shear times the sine of 2 theta. And now for our shear, we can do the exact same thing. I'm not going to walk through the whole analysis again, but I'll go ahead and write it out. So there you go. That's our equation for the shear as a function of the original setup. So your sigma x, your sigma y, and your shear. And a lot of the cases we looked at, most of these would be 0. So if you imagine like our axial loading on the bar, we would basically just have a sigma x. So this term would completely go away. This term would greatly simplify. And you'd also have your shear as a function of theta. But the reason that we went through all of this weird work to simplify and everything is because now we can ask the question of what is the maximum normal and shear stress that could possibly exist in this element at any angle of theta. And if you've taken calculus before, you know what we're about to do. We're about to take the derivative with respect to theta and then set it equal to 0 so we can get the critical points and then we can find the maximum. So we go ahead and do derivative of our normal stress with respect to theta. What we're going to get is that this first term is just going to go to 0. This second term is going to give us a negative sigma x minus sigma y sine of 2 theta, because our 2 is going to come out and cancel with this 1/2 because of the chain rule. The derivative of the cosine is negative sine. And then for the other term, we're going to get a plus 2 times our shear times the cosine of our 2 theta. Again, this 2 comes out because of the chain rule. And now we go ahead and we set this equal to 0. What we can do is we can add things across. So we get that our sigma x minus sigma y times sine of 2 theta has to equal 2 times the shear times the cosine of 2 theta. And now if we go ahead and we divide over this cosine and we divide over this sigma x minus sigma y, what we get is that the tangent of twice our theta, I'm going to call this theta p, which stands for principal, because our principal stresses are what we call the maximum and minimum stresses. Anyway, this has to equal our 2 times our shear in the xy all over our sigma x minus our sigma y. Now what we want to do is we want to plug this into our original sigma n, but of course we don't really know what the tangent is, right? The things that we actually need to plug in are cosine and sine. So we're going to do a little bit more trig right here to go ahead and get it into a form that we want to work with. So if we start with our sine squared plus cosine squared identity that we found earlier, let's just use x because why not? So cosine squared x has to equal 1. Now if we divide everything through by a cosine, then we'll get that the tangent squared of x, or I guess if you divide everything through by a cosine squared, my bad, plus 1 has to equal 1 over cosine squared of x. And now if we invert both sides, and then I guess I'm just going to write the cosine squared on this side because why not, equals 1 over 1 plus the tangent squared of x. And now I take the square root to get the cosine of x in terms of the tangent, which is what I'm really looking for, square root of 1 plus tangent squared of x. Boom. Okay. Now the sine of x, remember, is just equal to the cosine of x times the tangent of x, because the tangent of x is equal to sine over cosine. So if you multiply across by the cosine, And the reason this all the way goes back to opposite and adjacent, basically, right? So this is opposite over adjacent. This is opposite over hypotenuse over quantity, adjacent over hypotenuse. So our hypotenuses cancel. Anyway, going back here, this means that the sine of x is going to equal the tangent of x divided by the square root of, right, 1 plus tangent squared x. And now if we just let x be our 2 theta p, then we can go ahead and write sine and cosine in terms of all the stuff that we know, all right? So let's go ahead and start with sine. So our sine of 2 theta p is going to equal, we're just plugging stuff in here. So we'll have in the numerator the thing that we plugged in, sigma y. This should be a minus sign. Sigma y. And then we'll square root of 1 plus. And then if we take this squared, what we're going to get is 4 times our shear squared divided by sigma x minus sigma y as a quantity all squared, just like that. And now if we go ahead and bring this term down into here, what we'll get is that we'll get this is equal to twice our shear divided by square root of, now if I have this 1 over sigma x minus sigma y and I bring it into the square root, it's going to become squared and it's going to distribute across each of these terms. So I'm going to have sigma x minus sigma y quantity squared plus 4 times the shear squared, and then this is going to be inside the square root. And now what I'm going to do is I'm going to pull out this 4. So basically what I'm going to have to do is if I pull out a 4, I'm going to be left with this all over 4. This right here is going to be a 1, and when I take the 4 out of the square root, it'll become a 2. It'll cancel with this 2 up here. So this is going to give me the shear in the xy direction over square root of, now I could do sigma x minus sigma y squared all over 4, right? But notice I can bring this 4 into this squared as well. So I can say this is sigma x minus sigma y all over 2, and then I take this whole quantity and I square it. It's the same thing, and then I'll have plus shear in the xy squared. Okay? Now, for the cosine, I guess as I should just write, this is our sine, 2 theta p. For the cosine, it's going to be very similar. We're basically just going to have to take our sine and divide by the tangent. So if you recall, tangent of x equals sine over cosine. So therefore, x, or cosine x, has to equal sine x over tangent x. So our cosine of 2 theta p is just going to equal this quantity divided by the tangent. But remember that the tangent, if we come all the way back up here, is this right here. So basically, it's the same thing as our quantity down here, which is all this, divided by our 2 shear xy over sigma x minus sigma y. So when you go ahead and you invert that fraction, what you'll get is that the shear xy's will cancel. You'll have a sigma x minus sigma y in the numerator, and then your 2 will come into the denominator. So you have a 2 square root of, and then we just go ahead and write through all of this again. Square this plus our shear xy squared, okay? And now we have 2 quantities that we can plug in to this expression to get the maximum and minimum stresses, because remember we took the derivative and we set it equal to 0. So we go ahead and we plug these in. What we get is that our normal stress has to equal sigma x plus sigma y all over 2. And then we'll have plus sigma x minus sigma y all over 2 times the cosine. We just found the cosine. It's this big thing right here. Don't worry, it'll actually simplify quite a bit. There's a reason we did all of those identities earlier for the trig, is because it gets better. And then the form that it ends up in finally ends up giving us a really convenient way of actually like writing and thinking about all of this, which is why we went through all this trouble in the first place. Anyway, and then we'll also have our shear term times the sine of 2 theta p, which remember is this stuff right here. So let me go ahead and write that all in. We'll have our shear xy all over 2 quantity squared plus the shear squared, just like that. Okay, now here's what I want you to notice. Ignore the denominator of the square root and all of this for a second, okay? This second term right here in the numerator is going to be a shear xy squared, right? This term right here, we're going to have sigma x minus sigma y squared, because there's 2 of them, divided by 4. Does that remind you of anything? Because remember up here, when we had it divided by 4, we were able to bring it in. Maybe it wasn't right here. We brought it in to the square. So basically what we can do is we can rewrite this whole thing. I'm kind of running out of room to show this all on one screen. But this is sigma x plus sigma y over 2 plus, all right, now in the numerator, we'll have a sigma x minus sigma y quantity squared over 4, but I'm going to go ahead and rewrite this as sigma x minus sigma y over 2 squared, and then our denominator is going to be all of this square root of sigma x minus sigma y all over 2 squared plus this, right? Okay, now our second term is going to be shear xy squared all over this stuff. And notice that our numerator and our denominator are basically the same except for the power, right? Because if I combine this term and this term, I would have the exact same thing as the denominator, except it wouldn't have the square root. So basically, I have this whole stuff, all of this stuff inside the square root to the first power, divided by it to the 1/2 power, because that's what a square root is. So the power is 1 minus the 1/2 power, which means all of this combines to just be equal to this square root right here. So our final form is that sigma normal is going to be equal to sigma x plus sigma y all over 2 plus the square root of sigma x minus sigma y all over 2 squared plus our shear xy squared. So now, if we just have the original stress state, sigma x, sigma y, and our shear, we can find the maximum normal stress, and we can also find the minimum normal stress if we think about this tangent. So remember that our tangent has to equal 0, right? And so there are actually 2 solutions. We found the solution of theta p, right? If you think about the tangent graph, for every full rotation, which is a 2 pi, there are going to be 2 solutions that work for some y value, which means that the other solution to this is to add 180 degrees. Now, if you think about the sine and cosine function, right, if I go ahead and I have like my sine function, right, it's going to look something like this. It's going to go like that. So full period is this. This is 2 pi. A half period right here is pi. And now if you imagine if I invert this, or if I add 180, they're going to actually be the same effect. Because here, notice that it starts, it goes down and then up, and here it goes up and down. So the negative sign is actually the same as if I just started right here, and the same thing is true for cosine. So what I'm trying to say is that sine of some angle plus half a revolution is the same as the negative sine of that angle, and the same thing for cosine, which means that when we're adding the half a revolution, the only thing that's going to change is that this term right here is going to become negative, and this term right here is going to become negative. So when we add them in, we're going to have a negative sign right here and a negative sign right here, and that's going to transfer over to both of these terms. And when we combine them, the whole effect is that this square root is just going to be negative instead of positive. So now if we want the 2 principal or critical stresses, it's going to be this term plus or minus the square root of this term, where one of those will be the maximum and one of those will be the minimum, because remember we set the derivative equal to 0. All right, now if we think about what would happen if we were to plot these 2 states on a graph, or basically on one side we have the normal stress, and on one side we have the shear stress, as we're thinking about basically if this is our side and this is our angle, how is it going to look? Well, coming back to the normal stress right here, we can actually see that, let's just say we let theta equal 0, right? Well, if we know that theta equals 0, sine of 0 equals 0, which means both of these terms go away, the cosine of 0 is 1, so we actually just get it's equal to sigma x. So if we come over here to our plot, that's the wrong one. If we come over here to our plot, what we could do is we could plot basically sigma x, somewhere on here, let's just say it's like here, comma, our shear, right? And our shear will just come up to like, let's say right here. And then we'll have the center right here, something like this. So this right here will be our shear xy. And we can also do the same thing with 90 degrees, right? So at 90 degrees, the cosine is 0, so these two terms go away. The sine is 1, so we just get sigma y. So we could also plot on here sigma y. Let's just say it's like right here, right? And then we also have our shear right here. Boom. Shear. And we'd have something like this. And then it turns out, based on the relations between the shear and the normal stress, all of the possible states that we could get when we start changing the angle and looking at basically like the angular setup to our stress element, all of those will fit on this circle. So if you think about the principal stresses right here, those should occur at the maximum values of sigma. So right here and right here, right? So if you look, sigma x plus sigma y over 2, that's the average. That'll actually be right here. So I'll have sigma x plus sigma y all over 2. And then we add or subtract. All of this stuff right here is actually just the radius, if you think about it, right? So sigma x minus sigma y, that's this whole gap right here, divided by 2 will give me half of this gap. So either the length of this segment or the length of this segment. Then we're going to square that, add the height, square that, and then do a square root, which will give me the radius of this circle. So if I start here in the center and I add or subtract the radius, what I get are the two maximum and minimum, the two principal stresses. So we can go ahead and call this, let's call it sigma A and sigma B here just for now. Okay? And that also means that the maximum shear is actually just equal to the radius, or the value inside the square root right here. So this right here would be our shear max. And because it's equal to the radius, we could also say that our shear max just has to equal the diameter, which we can get as sigma A minus sigma B all over 2, right? Because it has to equal the radius. And now we can also, when we're talking about principal stresses, we can also have them in 3 dimensions. So if you recall, we assumed plane stress, which means basically we only have stresses in the xy plane, right? So we had our element right here. We have the x-axis and the y-axis. We have our normal stresses, so we'll have like a sigma x right here, right? And then we also have our vertical, so we'll have a sigma y right here. And then we have our shear, so we'll have like our shear, right? You remember this. But then this is really just a 2D projection of a 3D element, right? So in reality, we would have a cube that would look something like this. But the assumption that we made, because we only looked at the angle basically in 2 dimensions, is that everything outside the xy plane equals 0. So basically, if we imagine this is like our xy plane right here, this vertical is y, and then we have a z, we only have stresses basically in this direction right here. And it turns out that this is a pretty good approximation if we just have things that are like loads and forces that are acting in this plane, and if it's pretty thin, then things like bending aren't going to matter too much. And we could also have shears, right? So this would be like our shear here, and we'd have one here, and then we'd have the negative side, so this would go this way, and then this one would go this way. But technically, even though we're looking at this plane stress, it is still a 3D element. We're just assuming that it's 0 outside of the xy plane, which means that the third principal stress we would have is that this basically out of plane, this sigma z, has to equal 0. So just say sigma z has to equal 0. Because if you look at our circle right here, you can see that the maximum normal stresses occur where the shear equals 0, right? And so because we're assuming that there's no shear out of plane right here, right? We're assuming that there's no shear in this direction right here, or in this direction along basically around the y-axis or around the x-axis. We know that the z normal stress at 0 also has to be a principal stress. And so the sign convention, at least for this class, is basically to label the 3 normal principal stresses, which are the maximum stresses on that axis. So if you imagine I've got my x face right here, right? No matter how I rotate it, if I face it in any of these directions, or if I rotate it like this, the maximum stress that I'm going to get on that face is one of the principal stresses, and then I'll also have one for the y face and the z face, and we label them sigma 1, sigma 2, and sigma 3. And we also label them in descending order. So basically, sigma 1 would be our maximum total, sigma 2 would be like the medium value, and then sigma 3 would be the least. And each of these corresponds to one of the x, y, or z faces. So for example, let's say that I go ahead and I find my maximum and my minimum stresses in the plane, and I find something like sigma A equals 20 megapascals and sigma B equals, I don't know, let's say 10 megapascals. Well, then I know that my other principal stress is 0 megapascals, which means that my sigma 1 would be 20, my sigma 2 would be 10, and my sigma 3 would be this. But if, let's say, sigma B was a negative 10, then sigma 1 would be this, sigma 2 would be this, and sigma 3 would be this. And even though I'm assuming that there's no out-of-plane normal or shear stress, I could still rotate the element in those dimensions to see what would happen. So in reality, you would have basically the 3D version of Mohr's circle would look like this. So basically, we would have our y-axis and our x-axis right here. This is actually the sigma axis, and then the shear, the tau axis, and then we'd have a big circle, right? But this right here, let's just say this is the maximum circle, right? So this right here is the absolute maximum, and maybe in this case, we have this right here is our sigma A or sigma 1, and then this right here, we'll just say maybe it's the negative case. So the y-axis should be right here. So if our y-axis is basically in the middle like this, like let's just say it's right here, for example, okay? Then our minimum is actually negative. Why did it rotate like that? So my minimum shear stress in the plane is negative, and my maximum is positive here. Let's just say as an example. So this is sigma 1. This right here is sigma 3. Sigma 2 is the y-axis value, and that'll be somewhere around here. Or sorry, this right here is the z-axis out of plane, and it's equal to sigma 2. It's equal to 0, so it should actually be on the axis right here, essentially. But what I could do is I could also construct more circles that go in the different planes right here. So like this represents the z face, and this represents, let's just say it's the x face. So I could look here between the x and the z faces. I could rotate around, basically around the y-axis, and I would be able to create stress states rotating around them in between these 2 points. This is going to be hard. I should probably just sketch it. But basically, we'd be able to create a circle by rotating in around the y-axis and looking at the x and y faces. And then I could also have one here looking at rotating between the z-axis, the z face, and the y face. So basically around the x-axis in this direction right here. Sorry, it's a little bit more complicated in 3D. So yeah, that's an introduction to stress.